simplified equation. No, okay, so after we talk about this, what's the point of inducing all this charge? Remember here, we say we have the two-dimension electron gas. Okay, why we have two-dimensional electron gas? Because this is aluminum gallium nitride. This is gallium nitride. Again, I have negative charge here, right? If I maybe let me just draw here, right? I have negative fixed charge here, and then I have positive fixed charge at the top. That's why, and then plus the stress, I get a lot of 2DEG, right? Here, this is electron, right? This, I don't want you to get confused, is electron. And this is the two-dimension electron gas. And there is a HEMT, high electron mobility. We talked about the high electron mobility for gallium arsenide earlier, right? Now let's see how this forms. Look at this, because I have this net positive charge. When I do a cut on the band diagram here, A dash, A dash, right? Do you see that? Because I positive charge, I just bring this down. And then I get a lot of electron again. Last time I challenged you, right? Why I have a lot of electron here? Some people answer. Can some people answer again? Why I have a lot of electron at this point based on this band diagram?
It's because the gallium phase has negative charge on the top.
Say again.
Is it because of the gallium phase has negative charge on the top?
You have negative polarization charge on the top, and then we have a lot of positive polarization at the bottom of aluminum gallium nitride, right? So overall is actually positive charge, right? But there's a fixed polarization charge. But now, because of this fixed polarization charge, it pulled down the band, right? And then as a result, I claim that I have a lot of electron at this point. Why is that? Based on this band diagram.
Past the conduction band.
Huh?
You're into the conduction band?
What conduction band again? Can you say again?
You're into the conduction band?
Into the conduction band? Can you be more specific? Why this conduction band in this location means you have a lot of electron? Someone answered this last time in the gallium arsenide case. If you did not learn this class, I just give you this band diagram. Even in lecture 1, you should be able to tell me that there are lots of electron here. Why?
The conduction band's below the Fermi level.
Yeah, because EC, or let's say EF minus EC, is much larger than 0. Right? So I have a lot of electron, just like the gallium arsenide. So I have a lot of electron. What else? It only appears in this small triangular well. We call it well. So it's confined. So if it is confined, then this is a 2DEG. Two-dimension electron gas. And what else? No impurity. Last time when we talked about the gallium arsenide, we say all the impurity are in the barrier, so they don't get scattering. Here we don't have impurity. We only have this polarization charge. Polarization charge is not impurity. Look at, we don't have the figure now, right? Look at the old crystal. We did not introduce any fluorine atoms. It's all gallium nitride. The lattice is not distorted. So there's no impurity scattering. So it has high mobility. That's why it is a HEMT, high electron mobility transistor, right? So try to compare to gallium arsenide that we learned earlier. Is this okay? Any questions? if any doubts, please ask, right? Remember, many students did not speak out. Maybe it's not inconvenience or they don't like to discuss. But I think at least some also don't fully understand. So if you can help to ask, you are helping them. Do not feel that you are asking something stupid or whatever. There's no stupid question. Yes.
What's the difference between A and B? The figures?
Okay, great. Maybe I will hold on to answer this. Maybe I just finish this one first. Any other question related to how I draw this band structure? Right, we learned so much about gallium nitride. Eventually, we want to understand how the transistor works.
Professor, so the in HEMTs, the electrons are traveling. They aren't traveling through the material.
It's traveling. Okay. So, for example, I put 0 volt here, 5 volt here. Okay. Then the electron will travel from here to here. This is the cross section. This is source and drain, right? Then what does it mean? It means the electron here is traveling into the paper, into your screen, because this is AA is a vertical cut, right? So it's traveling into the screen. The source is at my face. The drain is behind the monitor, behind your screen. Make sense?
So the it has high mobility because is it still traveling through the gallium nitride, or is it traveling in between that, that interface?
It is, yes, it's high mobility because it is all traveling at this point into the screen, at this point. Okay, so along this whole line, it is this potential profile. Remember, this is a cut, vertical cut. So it's traveling into the screen at the same well, like what we are showing here. Yes, so you keep traveling inside the gallium nitride.
Professor? So basically, we are trying to say that gallium nitride has 2D Eg, that is electron gas. That's the reason the conduction band is below the Fermi level, and that is the reason we have a lot of electrons. Is that what we can say?
Yeah. So that's the reason we have a lot of electrons. But why we have this banding is because of the polarization charge, right? Because of the difference of the polarization charge between the barrier and the substrate. This is the substrate, right? We have done a lot of exercise to show that this one has a lot of negative, and this one, for this one is negative. Right? For this one, we are talking about this one now. A lot of positive on top and negative here. So overall, I have lots of positive charge. And because of this positive charge, I have this banding, so that I induce a lot of electron here. The reason I have a lot of electron is because of difference in polarization charge. And we calculated last lecture, 1e13 per cm square. Do I answer your question?
Yes, Professor. Thank you.
Okay, great. Now, you also ask why, what's the difference, right? Here you see I have gallium nitride, aluminum gallium nitride barrier. Here I add an insulator. This is not insulator. This is just a wide bandgap semiconductor. Here I may add oxide, get aluminum oxide, whatever. This is another style of doing this device. And this can have a few effects, for example, change the threshold voltage or reduce the gate leakage current. So this is just another type of HEMT. And sometimes they will call this MIS HEMT, sometimes, or MISH FET, just metal insulator semiconductor and then hetero field effect transistor. Okay, so this is a variation. So, but the theory is the same, except that when you draw the band diagram, you need to add the oxide band diagram. Okay. Now, based on this, right, if I apply zero bias to it, do I have current when I apply zero bias to the gate based on this?
No. We just have leakage current.
No, yes.
No. I apply 0 to gate bias to source, but I apply 5 volt to drain. Do I have current to the drain?
No.
Yes.
Okay, why no, why yes? How about yes first? Why yes? Why do you say yes?
You still have the 2D EG there. You need a more negative voltage to turn it off.
Exactly. Yeah. So the reason you see that as zero bias, do I see that this is zero bias band diagram? I have the conducting electron gas all the way from source to drain, right? 2D EG is there, right? For VG equal to 0, right? We show it already. So it is on, even you, right? Maybe I should draw even pointing to here. It is on, even you have zero bias. And you also give me the solution already. You say that we need VG smaller than 0 to turn it off. Okay, once you have VG smaller than 0, you start deplete away the electron, right? When you have 0, remember, when you have a negative bias, you pull up the band, right? So you lift it up, as a result, your conduction band is not below the Fermi level again. Okay, and this is called normally on. Okay, if you're doing power converter, this is a big deal. Do you know why that is a problem? Your gallium nitride is sustaining maybe 1000 volt, but not here, maybe 600 volt when it is at off state, right? You need to apply a negative gate voltage. What if there's a circuit failure? You don't know when it failed, right? If circuit failure, this bring to 0 volt, then your transistor is going to turn on under 600 volt. It's going to burn a lot of hazard, fire, or the whole system breakdown. So for normally off device, you need the so-called gate safe. I suddenly forgot the name. Something safe circuit in the gate circuit.
Or like a sequencer?
Say again?
Like a sequencer?
Sequencer? I don't know what is sequencer. You mean the circuit to prevent it from going to negative, right? Anyway, just a circuit that for safety operation, so that if your circuit fail, the control circuit fail, the digital circuit controlling this one fail, it won't give it 0. Otherwise, it's going to turn on the transistor. Your transistor is switch, sustaining 600 volt, and you suddenly fail, then it's a disaster, right? So you need to have a gate safe drive to avoid this one to go to 0 if something goes wrong. If you are normally off, usually if it fail, everything go to 0, then it doesn't matter, right? You just your transistor is still off. But now, in order to make it off, I need to make it, for example, negative 5 volt. If my control chip fail, it might not stay at negative 5 volt. It can go to 0 volt. Then that would be a problem. Okay, that is something you will need to handle if you're doing power electronics. Okay, any questions?
I have a question about the structure. Like if we say flip the phase and we induce a 2D HG, does it make a high hole mobility transistor?
It does, yeah.
But we don't see it. Is it because the mobility in gallium nitride is low?
Yeah, hole is smaller because of higher effective mass. But we do see this, but usually we use gallium phase. Nowadays, people, if you remember, there was an article of the day, I show you a 2D HG, they actually use nitrogen phase. You see Santa Barbara. And because when they use hole, or maybe I was wrong, sorry, that is nitrogen phase, but they still introduce electron by using this another stress, by putting the gallium nitride on top. So I was wrong, but they do have hole. Yeah, people do hole, but yes, you're right. The conductivity is worse, not as good as the electron. But we use this for other purpose. We do use that. There's something called superjunction. We have multi-layer of electron hole, electron hole, electron hole. They have special purpose. Okay.
Okay, thank you.
Yeah, good question, right? So what I'm teaching is limited, right? So here are lots of combination, just like Lego. Play with that, and you find a lot of interesting things. Now, before I finish